Imagine, for a moment, standing at the very edge of everything. Not on a cliff, not on a beach, but at the boundary between the known and the unknown, where the sky meets the sea in a perfect, unbroken line. Ahead of you, nothing. No land. No horizon. Just an endless drop into the void. This is not a dream. This was, for many centuries, a widely accepted reality. To sail too far west was to risk falling off the edge of the world. And not because people were foolish, but because they believed, with the full weight of observation, reason, and divine authority, that the earth was flat. It's easy from our modern vantage point to smile at this idea, to picture medieval scholars arguing over maps with dragons drawn at the margins, warning sailors of doom. But we misunderstand the past if we assume this belief was born of ignorance. On the contrary, the flat earth was a scientific model, an attempt to make sense of the world through the tools available at the time. It was logical. It was consistent. And for a long while, it worked. The sky arched above like a dome. The ground stretched out beneath like a plain. The sun rose in the east and set in the west, moving across the heavens in a predictable arc. The stars rotated in perfect circles around a fixed point. All of this supported the idea of a flat, motionless earth at the center of a celestial sphere. The evidence, as they saw it, was all around them. You could walk in any direction and never feel a curve. You could look across a lake and see the distant shore without any distortion. The world, to the senses, appeared flat. And so, the conclusion seemed inescapable. But here's the unsettling truth: the flat earth wasn't just a primitive myth. It was a theory. And like all scientific theories, it was built on observation, tested through experience, and refined over time. Ancient civilizations, Babylonians, Egyptians, early Hebrews, saw the earth as a flat disk floating in an infinite ocean, surrounded by waters above and below. The firmament, a solid dome, held back the celestial waters, and the stars were embedded in it like jewels. This wasn't fantasy. It was cosmology. It was the best explanation for the universe they could construct. Even in ancient Greece, where philosophy and mathematics flourished, the idea of a flat earth persisted for generations. It wasn't until the 6th century BCE that a radical shift began. A man named Pythagoras, known more for his theorem than his cosmology, proposed something extraordinary: that the earth was spherical. Why? Not because he had seen it from space, not because he had circumnavigated it, but because he believed the sphere was the most perfect shape. To Pythagoras, beauty and symmetry were not just aesthetic ideals, they were signs of truth. The gods would not create a flawed, angular world. They would create a sphere. This was not science as we know it today. It was metaphysics. Aesthetic reasoning. But it planted a seed. Later, around 350 BCE, Aristotle offered the first empirical arguments for a round Earth. He noticed something peculiar during lunar eclipses: the shadow that the Earth cast on the moon was always curved. And not just curved, consistently circular, no matter the time or location of the eclipse. The only shape that always casts a circular shadow, regardless of angle, is a sphere. A flat disk would sometimes cast an oval shadow. But the Earth's shadow was always round. That was compelling. He also observed that as travelers moved south, new stars became visible on the horizon, while familiar northern constellations dipped lower and eventually disappeared. If the Earth were flat, the entire sky should be visible to everyone, everywhere. But it wasn't. Different latitudes saw different skies. The simplest explanation? The surface of the Earth was curved. Still, these ideas remained controversial. The notion of a spherical Earth challenged not only perception but also common sense. If the Earth were round, why didn't people on the opposite side fall off? Why didn't water pour off the edges? How could gravity work on a sphere? These were legitimate questions. And without a theory of gravity, they were difficult to answer. It wasn't until the 3rd century BCE that a man named Eratosthenes, librarian of Alexandria, did something astonishing. He measured the Earth's circumference. Using nothing but sticks, shadows, and geometry, he calculated the planet's size with remarkable accuracy. On the summer solstice, he noticed that in the city of Syene, modern-day Aswan, the sun shone directly down a deep well, casting no shadow at noon. But in Alexandria, about 800 kilometers to the north, a vertical stick cast a small shadow, about 7.2 degrees from vertical. Knowing the distance between the two cities, he used simple trigonometry to estimate the Earth's circumference. His result? Approximately 40,000 kilometers. The actual value is about 40,075 kilometers. He was off by less than 2%. This was not luck. This was science. And yet, even with such evidence, the spherical Earth did not become common knowledge. For centuries, the idea remained confined to scholars, philosophers, and mathematicians. The general public, the sailors, the farmers, the kings, they continued to live in a world that felt flat, looked flat, and was described in religious texts as flat. And here lies one of the deepest tensions in human understanding, the conflict between direct experience and abstract reasoning. We trust our senses. We believe what we see. But the universe often deceives us. The sun appears to move around us. The ground feels solid and level. The horizon looks straight. These observations are not false, they are limited. They are local truths, not global ones. The flat Earth model wasn't wrong because people were stupid. It was wrong because it was incomplete. It worked well enough for daily life, for navigation over short distances, for planting crops and building cities. But it failed when pushed to its limits. When explorers began to sail farther, when astronomers studied the heavens in greater detail, when mathematicians applied logic to observation, the model began to crack. Still, the resistance to change was profound. Not because of science, but because of identity. To admit the Earth was round was to admit that everything else might be uncertain. It was to question authority, religious, political, intellectual. If the Earth wasn't as the scriptures described, what else might be misinterpreted? If the sky wasn't a dome, what held the stars in place? The spherical Earth wasn't just a new shape, it was a new worldview. And so, for centuries, the idea lingered in the shadows of academia, accepted by some, rejected by many. Even in the Middle Ages, educated Europeans, those who read Greek and Roman texts, knew the Earth was round. The myth that medieval people believed in a flat Earth is itself a myth, largely invented in the 19th century to portray the past as dark and superstitious. In reality, by the time of the Renaissance, the spherical Earth was widely accepted among scholars. But acceptance is not the same as proof. And that's where the real turning point came, not in a library, not in a lecture hall, but on the open sea. In 1519, Ferdinand Magellan set out with 5 ships and over 200 men on a voyage to find a western route to the Spice Islands. He didn't set out to prove the Earth was round, everyone who mattered already believed that. He set out to circumnavigate it. To sail around the world. Magellan never completed the journey. He was killed in the Philippines in 1521. But one ship, the Victoria, under the command of Juan Sebastian Elcano, continued westward. 3 years after departure, with only 18 survivors, the Victoria returned to Spain. They had sailed west and come back from the west. They had kept going, and the world had not ended. They had not fallen off. Instead, they had looped around it. This was not a philosophical argument. This was empirical proof. The Earth was not just a mathematical abstraction. It was a physical reality you could sail around. The voyage didn't just confirm the Earth was round, it made it undeniable. It transformed the idea from theory to lived experience. And yet, even then, the implications took time to settle. The world had turned, but human perception lagged behind. We still speak of the sun rising and setting, even though we know it doesn't move around us. We still feel the ground is flat beneath our feet, even though we know it curves. Our senses have not changed. Only our understanding has. This moment, the moment science admitted it was wrong, not once, but gradually, over centuries, is more significant than it first appears. It reveals something fundamental about the nature of knowledge, that it is provisional. That even our most certain beliefs are subject to revision. That truth is not a destination, but a process. Because if we could be so wrong about the shape of the Earth, something so visible, so tangible, so seemingly obvious, what else might we be wrong about? Consider dark matter. We cannot see it. We cannot touch it. But we infer its existence from the way galaxies rotate. Without it, the math doesn't work. So we say it's there. But what if we're wrong? What if, centuries from now, scientists look back and say, they thought most of the universe was made of invisible matter? How quaint. They just didn't understand gravity. Just as we now look back and say, they thought the Earth was flat. How quaint. They just didn't understand perspective. Or consider consciousness. We know it exists, we experience it every moment. But we have no agreed-upon theory for how it arises from matter. Is it an emergent property of complex brains? Or something more fundamental? Could it be that future generations will laugh at us for thinking the mind was confined to the skull, when in fact it's woven into the fabric of the universe itself? The flat Earth was not a failure of science. It was a success. Because science, at its best, is not about being right. It's about being willing to be wrong. It's about following the evidence, even when it leads to uncomfortable conclusions. It's about humility in the face of the unknown. And perhaps that's the most soothing thought of all. In a universe so vast, so mysterious, so full of paradoxes and unanswered questions, it's okay not to have all the answers. It's okay to be wrong. Because being wrong is how we learn. Being wrong is how we grow. So as you lie here, listening, let your mind drift over the curvature of the Earth. Imagine the Victoria, small and fragile, sailing into the unknown. Imagine the fear, the wonder, the quiet realization that the world was round all along. And now, let yourself rest in that same uncertainty. What feels solid beneath you may be an illusion. What seems obvious may be incomplete. And that's all right. You don't need to hold on to certainty. You don't need to defend your beliefs. You can simply let them float, like clouds across a vast sky. Because the truth is not something you grasp. It's something you approach, slowly, humbly, over a lifetime. And if the Earth could turn beneath our feet, so too could time itself stretch and bend. From the solid ground of our planet, we now drift into the warping fabric of reality, where time isn't constant, but fluid. Next, we confront the theory that rewrote time, Einstein's relativity. Imagine, for a moment, two children born on the same day, in the same hospital, under the same stars. They grow up side by side, playing in the same yard, sharing the same birthday cake, whispering secrets in the dark. Then, one day, one of them climbs into a spacecraft and launches into the cosmos, hurtling through space at nearly the speed of light. The other stays behind, watching the stars from the safety of Earth. Decades pass. The traveler returns. They embrace. But something is off. The one who stayed behind has gray hair, wrinkled hands, the slow breath of age. The one who journeyed through the void looks barely older than the day they left. They are the same age, biologically, genetically, but time has treated them differently. Not by chance. Not by fate. By the cold, unyielding laws of physics. This is not a fairy tale. It's not science fiction. It's called the twin paradox, and it is one of the most profound, unsettling consequences of Einstein's theory of relativity. It reveals a truth so deeply counterintuitive that it feels like a violation of reality. Time is not what we thought it was. It is not a universal clock ticking steadily in the background of existence. It does not flow at the same rate for everyone, everywhere. Time is not absolute. It is relative. It bends. It stretches. It slows. And in doing so, it unravels one of the most fundamental assumptions of human experience. For centuries, time was seen as a river, constant, unchanging, flowing forward at the same pace for all. Isaac Newton, the father of classical physics, described time as absolute, true, and mathematical, flowing uniformly without relation to anything external. It was the stage upon which the universe played out its drama. Events happened in time, but time itself remained untouched, impartial, eternal. Sunrise, sunset, the ticking of a clock, the beating of a heart, all of it marched to the same rhythm, everywhere in the cosmos. But in 1905, a young patent clerk in Bern, Switzerland, shattered that illusion. Albert Einstein, working in quiet solitude, published a paper that would forever change our understanding of reality. His theory of special relativity revealed that time is not separate from space. It is woven into it. Together, they form a single fabric, space-time. And just as space can be warped by mass and energy, time can be distorted by motion and gravity. The key insight was simple, yet devastating in its implications. The speed of light is constant. No matter how fast you move, light always travels at 299,792,458 meters per second. You cannot catch up to it. You cannot see it moving slower. This constancy forces a strange trade-off. If light's speed never changes, then something else must give. And that something is time. Here's how it works. Imagine you're on a train moving at nearly the speed of light. You shine a flashlight toward the ceiling. To you, the light goes straight up and bounces straight down. But to someone standing outside the train, watching it race by, the light doesn't just go up and down, it traces a diagonal path, because the train is moving forward as the light travels. That diagonal path is longer than the vertical one. Since light must travel at the same speed for both observers, and the outside observer sees it covering more distance, the only way for the math to balance is if time itself slows down for the person on the train. From the outside, your clock appears to tick slower. Your heartbeat, your thoughts, your aging, all of it stretches out, as if the universe itself is breathing more slowly for you. This is not an illusion. It is real. It has been measured. Atomic clocks flown on airplanes run slightly slower than identical clocks on the ground. Particles called muons, created in the upper atmosphere, should decay before reaching Earth's surface, but because they're moving so fast, time dilates for them, allowing them to survive the journey. Without relativity, they wouldn't make it. With it, they do. And gravity does the same thing. Einstein's general relativity, published in 17, showed that massive objects like planets and stars warp the fabric of space-time. The stronger the gravity, the more time slows down. A clock at the top of a mountain runs slightly faster than one at sea level, where gravity is stronger. GPS satellites, orbiting high above Earth, experience time about 38 microseconds faster per day than clocks on the surface. If engineers didn't correct for this, GPS systems would be off by kilometers within minutes. The fact that your phone can pinpoint your location with such accuracy is not just a triumph of engineering, it's daily proof that time is not absolute. So what does this mean for us? That time is not a single, unified flow, but a personal experience. Each of us carries our own clock, ticking at a rate determined by how fast we move and how deep we are in a gravitational well. There is no now that everyone shares. No universal present. When you look at the stars, you're seeing them not as they are, but as they were, some of them thousands, even millions of years ago. And from their perspective, you are the one in the past. There is no privileged moment. No cosmic now. This leads to one of the most mind-bending ideas in physics, the block universe. In this view, time does not flow at all. Past, present, and future all exist simultaneously, like frames in a film reel. We are not moving through time, we are in time, like a character embedded in a single frame of a movie. The sensation of time passing, of the present moment slipping into the past, may be nothing more than a feature of consciousness, not of reality itself. Think of a book. All the pages exist at once. Chapter 1, Chapter 10, the final page, they're all there, bound together. But you can only read one page at a time. You turn the pages, and it feels like the story is unfolding, like the future is being created as you go. But the ending was written long ago. In the block universe, your birth, your first kiss, your last breath, all of it is already there, fixed in the four-dimensional geometry of space-time. You are not becoming. You are being, across time, like a long, continuous thread woven through the fabric of existence. This raises profound questions about free will. If the future already exists, are your choices real? Or are they just the inevitable unfolding of a predetermined structure? Are you the author of your life, or merely a reader of a script you didn't write? Some physicists argue that the block universe doesn't negate free will, it just redefines it. Your choices are still yours, even if they are part of a larger, unchanging structure. The path is fixed, but you still walk it. The meaning comes from the journey, not the destination. But the deeper we go, the more the ground beneath us seems to shift. If time is relative, then causality, the idea that cause must come before effect, can become fragile. In extreme cases, like near black holes or at relativistic speeds, the order of events can appear to reverse for different observers. Though no information can travel faster than light, the perception of time can create paradoxes. What if, from one perspective, you see a person die before they are born? The math allows it, even if logic rebels. And yet, the universe holds. It does not break. Because relativity also ensures that no observer can ever witness an effect before its cause in their own reference frame. The laws of physics are preserved, even as time itself becomes fluid. It's as if the universe has built-in safeguards, like a dream that never quite collapses into nonsense, no matter how strange it becomes. Now, let your mind rest on this, the now you are experiencing, the soft breath in your chest, the distant hum of the world outside, the quiet rhythm of your thoughts, is not shared by anyone else in exactly the same way. Your present is slightly out of sync with the person next to you, with the stars above, with the pulse of the cosmos. You are each living in your own pocket of time, drifting through space-time at your own pace. Can you feel it? Not in your mind, but in your body? The subtle, imperceptible stretching of moments? The way time slows when you're still, speeds up when you're moving? The way a minute in pain feels like an hour, while an hour of joy vanishes in a blink? Even our subjective experience echoes the physics. Time is not just external. It is internal. It is shaped by motion, by gravity, by emotion, by attention. And perhaps that is the most soothing realization of all. If time is not rigid, if it is malleable, then the pressure to keep up with it begins to dissolve. You do not need to race against the clock, because the clock is not the same for anyone. You are not behind. You are not late. You are simply here, in your own stream of time, moving at your own pace through the unfolding of your life. Let that thought linger. Let your breath slow. Feel the weight of time not as a chain, but as a current, gentle, variable, carrying you forward even when you feel still. Because if the earth could turn beneath our feet, so too could time itself stretch and bend. From the solid ground of our planet, we now drift into the warping fabric of reality, where time isn't constant, but fluid. Next, we confront the theory that rewrote time, Einstein's relativity. Close your eyes. Picture a coin suspended in midair, spinning endlessly. You cannot see which side is up. It's not that you're refusing to look, it's that the coin hasn't decided yet. It is not heads. It is not tails. It is, in some unfathomable way, both. Not in your imagination, not as a metaphor, but as a physical reality. This is not magic. This is not philosophy. This is the world of quantum mechanics, a realm so strange, so counterintuitive, that even its discoverers struggled to believe it. And at the heart of this mystery lies a concept so unsettling that it challenges the very foundation of what we mean by reality, superposition. In the classical world, the world of trees, cars, and falling apples, things are what they are. A cat is alive or dead. A light is on or off. A particle has a position and a velocity. But in the quantum world, none of this holds. At the smallest scales, particles do not behave like tiny billiard balls. They behave like waves of possibility. An electron does not have a definite location until you measure it. It exists in a haze of potential, spread out across space, occupying multiple states at once. It is here and there. It is moving fast and slow. It is, in essence, everything it could be, until the moment you look. The most famous demonstration of this is the double-slit experiment, a deceptively simple setup that has haunted physicists for over a century. Imagine a barrier with two narrow slits cut into it. Behind it, a screen that records what passes through. Now, fire tiny particles, electrons, one at a time, toward the slits. If electrons were purely particles, like bullets, you'd expect them to go through one slit or the other and leave two distinct clusters on the screen. But that's not what happens. Instead, an interference pattern emerges, alternating bands of high and low intensity, like ripples overlapping in a pond. This is the signature of waves. Somehow, each electron behaves as if it passed through both slits at once, interfering with itself like a wave. Even more astonishing, this happens even when electrons are sent one by one, with long pauses between them. There is no other electron to interfere with. And yet, the pattern builds up over time, as if each individual electron carried the memory of a wave, spreading through both paths simultaneously. Now, here comes the twist. Place a detector at one of the slits to observe which path the electron takes. The moment you do this, the moment you look, the interference pattern vanishes. The electrons suddenly behave like particles again, forming two clean bands behind the slits. The act of observation has changed the outcome. It's as if the electron knows it's being watched and decides to play by different rules. This is not a flaw in the experiment. It has been repeated countless times, with photons, atoms, even large molecules. The result is always the same. When no one is looking, reality remains in a state of possibility. When someone looks, it collapses into a single, definite outcome. Observation does not merely reveal reality, it participates in creating it. This is the core of the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, a quantum system exists in a superposition of all possible states until it is measured. The act of measurement forces the system to choose one outcome, collapsing the wave function into a single reality. But what counts as a measurement? Is it a conscious observer? A camera? A single atom bumping into another? The theory doesn't say. It simply works. And that has been enough for many physicists to use quantum mechanics with incredible success, powering technologies like lasers, transistors, and quantum computers. But it leaves a deep, unsettling question: what is reality, if it depends on being observed? To illustrate the absurdity of this idea at human scales, Erwin Schrödinger proposed a thought experiment in 1935. Place a cat in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the Geiger counter triggers the hammer, which breaks the vial, killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, the atom exists in a superposition of decayed and not decayed, so the cat must be in a superposition of alive and dead until someone opens the box. Schrödinger didn't believe this was possible. He meant it as a reductio ad absurdum, a way of showing how ridiculous the Copenhagen interpretation seemed when applied to everyday objects. But decades later, physicists still debate whether the cat is truly both alive and dead, or whether something deeper is at play. Because the implications of quantum superposition go far beyond electrons and cats. They strike at the nature of existence itself. If observation collapses the wave function, then consciousness may play a fundamental role in the universe. Are we passive spectators of a pre-existing reality? Or are we, in some way, co-creators of it? Some interpretations of quantum mechanics flirt with this idea. The von Neumann-Wigner interpretation, for example, suggests that consciousness is the ultimate cause of wave function collapse. In this view, the universe remains in superposition until a conscious mind observes it. Reality, then, is not complete without a witness. This is a deeply unsettling idea. It suggests that the universe was in a state of quantum ambiguity until the first conscious being evolved to observe it. Or worse, that without observation, nothing truly exists. It echoes ancient philosophical and spiritual traditions that claim reality is an illusion, a dream, or a projection of mind. But now, it comes not from mysticism, but from the most rigorously tested theory in science. Yet many physicists resist this conclusion. It feels too subjective, too anthropocentric. How can the entire universe depend on human observation? What about before life evolved? Did the moon exist when no one was looking at it? Einstein famously mocked this line of thinking, asking whether he really believed the moon was only there when he looked at it. Most scientists today agree that measurement does not require consciousness, that any interaction with a larger system, such as a detector or even the environment, can cause decoherence, the process by which quantum superpositions leak away into classical definiteness. Still, the boundary between quantum and classical remains blurry. Why do large objects not exhibit superposition? Why don't we see tables, chairs, or people in multiple states at once? One answer is decoherence, the constant interaction with the environment. Air molecules, photons, thermal vibrations, washes out quantum effects almost instantly in large systems. But recent experiments have pushed the limits. Scientists have placed tiny mirrors, electric currents, and even small diamonds into superposition states, visible to the naked eye under certain conditions. The line between the quantum and the classical is not as sharp as we once thought. And then there is the many worlds interpretation, proposed by Hugh Everett in 1957. It offers a radical alternative: nothing collapses. Superposition never ends. Every possible outcome of a quantum event actually occurs, but in separate, branching universes. When you open Schrödinger's box, the universe splits. In one branch, the cat is alive. In another, it is dead. Both are real. Both exist. You, too, split, becoming two versions of yourself, each experiencing one outcome. There is no collapse, no special role for observation. Just an ever-branching multiverse, where every quantum possibility is realized. This interpretation avoids the need for consciousness or mysterious collapses. But it comes at a cost: an infinite number of unseen realities, each as real as our own. How many versions of you are out there? One who took a different job. One who said yes instead of no. One who never existed because a single atom decayed a millisecond earlier. The mind reels at the scale of it. And yet, many physicists find it more elegant than the alternatives, because it removes the arbitrary divide between observer and observed. But here's the deeper mystery: we don't know which interpretation is correct. All of them make the same predictions. All are consistent with the mathematics. The choice between them is not scientific, but philosophical. It depends on what you're willing to believe about reality, consciousness, and the nature of existence. And so, we return to the quiet, meditative question: are you the observer, or are you being observed? Because if observation shapes reality, then every time you look at the world, you are not just receiving information. You are participating in a cosmic act of creation. The tree you see, the star you gaze upon, the breath you feel in your chest, each moment of awareness may be the point at which potential becomes actual. Not because the universe is watching you, but because, in some profound way, the universe is you. Let that thought settle. Let your breath slow. Feel the stillness between thoughts, where the world is not yet decided. In this moment, before the next sensation arises, before the next sound reaches your ear, what is real? Is it the chair beneath you, the air in your lungs, the pulse in your wrist? Or is it the infinite web of possibilities, shimmering just beneath the surface, waiting for your attention to bring it into form? Because in the quantum world, nothing is certain. Nothing is fixed. And that, perhaps, is the most peaceful truth of all. You do not need to hold on to what is. You can simply rest in what could be. And as you drift, let the boundaries of self and world soften, like ripples fading into still water. From the quantum world, where nothing is certain, we return to biology, where life itself was once thought to arise spontaneously. But maggots don't come from meat. Or do they? Next, the myth of spontaneous generation. There was a time when life seemed to rise from nothing. Not in the distant, mythical past, but in the everyday world, on kitchen counters, in barns, in forgotten corners of the cellar. A piece of meat, left out for a few days, would begin to writhe with tiny white worms. No one had placed them there. They simply appeared. A pile of grain, mixed with damp rags, would, after a week, teem with mice. No parents had been seen. No footprints. Just life, emerging from stillness. This was not magic. It was not superstition. For centuries, this was accepted as scientific fact. Life could generate spontaneously from non-living matter. The idea was so intuitive, so consistent with observation, that it shaped medicine, philosophy, and even theology. But then, one man, working in a quiet laboratory in Paris, sealed a flask with a long, curved neck and changed everything. Louis Pasteur did not set out to rewrite the origins of life. He was a chemist, a microbiologist, concerned with wine and beer spoilage, with fermentation, with disease. But in the mid-19th century, the debate over spontaneous generation was raging. Scientists were divided. Some believed that under the right conditions, heat, moisture, decay, life could emerge anew from inert matter. Others insisted that life only came from life. The question was not merely academic. It struck at the heart of what life was. Was it a special force, a divine spark? Or was it just chemistry, given form? Pasteur's genius was in his simplicity. He took flasks filled with nutrient-rich broth, something that would quickly grow mold and bacteria if exposed to air. But instead of sealing them completely, he bent the necks into long, graceful curves, like swans' necks, allowing air to enter, but trapping dust and microbes in the bend. The air could flow in, carrying its invisible currents, but the tiny organisms floating in it could not reach the broth. The flasks remained clear, sterile, lifeless. Meanwhile, identical flasks with straight necks, open to the air, quickly clouded with microbial growth. The difference was undeniable. Life did not arise from the broth itself. It came from outside, from the air, from dust, from invisible seeds carried on the wind. When Pasteur tilted a swan-necked flask, letting the broth touch the trapped sediment, it too became contaminated. The moment the microbes gained access, life exploded into being. In that instant, spontaneous generation, the idea that life could emerge from non-life under everyday conditions, was dead. Biogenesis, the principle that life arises only from pre-existing life, had been proven. The scientific community, after years of debate, could no longer deny it. Pasteur had not just conducted an experiment. He had closed a door on a worldview that had stood for millennia. And yet, in closing that door, he opened another, one far more mysterious. Because if life does not just appear, then where did it come from? If every living thing descends from another living thing, then who was the first? At some point, long ago, in the silent depths of a young earth, non-living matter must have given rise to life. There was no other option. The first cell could not have had a parent. It had to have emerged from chemistry. And so, science was left with a paradox. Life does not arise from non-life, except, of course, when it does. This is the riddle of abiogenesis, the origin of life from non-living matter. It is not spontaneous generation as the ancients imagined it. No one believes mice come from rags anymore. But the deeper question remains, how did the first self-replicating, metabolizing, evolving system arise from a world of rocks, water, and gas? What bridge exists between the inert and the animate? Between chemistry and biology? To understand the enormity of this question, imagine a world without life. The Earth, 4 billion years ago. No trees. No insects. No oceans teeming with fish. Just a planet of volcanic rock, steaming vents, lightning storms, and vast, shallow seas. the atmosphere thick with methane, ammonia, carbon dioxide. No oxygen. No ozone. The sun, younger and dimmer, casts a pale light. And in this harsh, alien world, something impossible happens. A molecule forms that can make a copy of itself. Not perfectly. Not always. But often enough. And when it fails, the errors sometimes lead to something better. And so, evolution begins. Not of species, but of molecules. This is the threshold science struggles to cross. We can trace life backward through fossils, through DNA, all the way to the last universal common ancestor, a single-celled organism from which all life on Earth descends. But before that, silence. A gap. A moment not recorded in stone, but lost to time. In 1953, Stanley Miller and Harold Urey attempted to recreate that moment. They built a closed system of flasks and tubes, simulating the early Earth, water, methane, ammonia, hydrogen. They added heat. They sent electric sparks through the mixture, simulating lightning. And after days, they found something astonishing. Amino acids, the building blocks of proteins, had formed. Life's ingredients, created from non-life. It was a revelation. For the first time, the idea that life could emerge from chemistry seemed not only possible, but plausible. Since then, scientists have discovered amino acids in meteorites, in interstellar clouds, even in the icy plumes of Saturn's moon Enceladus. The universe, it seems, is rich with the raw materials of life. But having the ingredients is not the same as baking the cake. The leap from amino acids to a self-replicating system is vast. A protein is not alive. A strand of RNA is not alive. But together, in the right configuration, they might become something that acts alive. Some theories suggest that RNA came first, capable of both storing information and catalyzing chemical reactions. In the RNA world hypothesis, early life was based not on DNA and proteins, but on RNA molecules that could copy themselves, evolve, and eventually give rise to more complex systems. Other ideas point to hydrothermal vents on the ocean floor, cracks in the Earth's crust where hot, mineral-rich water meets the cold sea. These environments provide energy, chemical gradients, and microscopic pores in rock that could have acted as natural cell membranes, concentrating molecules and allowing them to interact. In these dark, hidden places, far from sunlight, life may have begun not with a spark, but with a slow, rhythmic pulse of chemistry, building complexity over millions of years. There are even more radical ideas. Panspermia suggests that life didn't originate on Earth at all, that it arrived from space, carried on comets or asteroids. But this only moves the problem elsewhere. If life came from Mars, or from a distant star system, we still have to ask, how did it begin there? And then there is the deeper philosophical question, what is life? We know it when we see it, but defining it is surprisingly difficult. Is it self-replication? Metabolism? Evolution? Consciousness? A virus can replicate and evolve, but most scientists don't consider it alive because it can't metabolize on its own. A crystal can grow and replicate its structure, but it doesn't evolve. Life seems to be a process, a dynamic, far from equilibrium state maintained by a constant flow of energy. Perhaps life is not a thing, but a pattern. A dance of molecules that maintains itself, adapts, persists. And if so, then maybe it is not as rare or miraculous as we think. Maybe, given the right conditions, chemistry naturally tends toward complexity. Maybe life is what matter does when it has enough time, enough ingredients, and enough energy. But we still don't know. the gap between non-life and life remains one of the greatest unsolved mysteries in science. And that uncertainty is not a failure. It is a reminder of how much we still have to learn. Because Pasteur's flask did more than disprove spontaneous generation. It taught us humility. It showed that even the most obvious truths, maggots from meat, mice from grain, could be illusions. It revealed that the world is not always as it appears. That life does not arise easily. That it is precious, fragile, and deeply interconnected. And in that fragility lies a kind of beauty. Imagine the first moment, somewhere, in the darkness of a primordial pool, a molecule folded just right, touched another, and made a copy. No fanfare. No light. Just chemistry, stumbling into something new. And then again. And again. And over eons, that simple act gave rise to forests, to oceans, to consciousness, to you. Can you feel the silence between non-living molecules and the first spark of life? Not the silence of emptiness, but the silence of potential. The quiet before the first breath. The stillness in which something new hesitates, trembles, and then, against all odds, begins. It is a silence we can never truly hear, because it happened long before ears evolved. But we carry it within us. In every cell, in every strand of DNA, we are made of that moment. We are the continuation of that first, improbable spark. And so, as you lie here, breathing slowly, heart beating in the dark, remember this: you are not separate from that mystery. You are its expression. The universe, once silent and lifeless, now dreams through you. It looks through your eyes. It wanders through your mind. And perhaps, in some quiet corner of a distant planet, the same process is beginning again, molecules drifting, colliding, hesitating, on the verge of becoming something more. Let that thought linger. Let your breath soften. Feel the ancient chemistry in your blood, the echo of that first replication in your cells. You are not just alive. You are the universe remembering how to live. And if life didn't just appear, perhaps the universe didn't either. Once, we thought it was eternal. But then, a single observation changed everything. Next, the Big Bang, and the moment science discovered time had a beginning. For nearly all of human history, the universe was imagined as eternal. Not just old, infinite. Not just vast, unchanging. The stars were fixed in their courses, the heavens turning in perfect, timeless cycles. The earth might age, civilizations might rise and fall, but the cosmos itself endured, forever. It had no beginning. It would have no end. This was not mere poetry. It was philosophy. It was theology. It was science. From the ancient Greeks to the medieval scholars, from Eastern cosmologies to Enlightenment thinkers, the idea of an eternal universe was as natural as the air we breathe. To suggest otherwise seemed not just incorrect, but almost blasphemous, a violation of the natural order. And then, in the quiet glow of a telescope's eyepiece, everything changed. In the 1920s, at the Mount Wilson Observatory in California, an astronomer named Edwin Hubble made a discovery so profound it would rewrite the story of existence. He was studying distant galaxies, measuring their light, their distance, their motion. And what he found defied all expectation: the galaxies were not standing still. They were moving away from us. And not only that, the farther away they were, the faster they receded. It was as if the universe itself was stretching, like dough rising in an oven, carrying galaxies apart like raisins in expanding bread. This was not an explosion into space. It was space itself that was growing. The fabric of reality was unfolding, moment by moment, carrying everything with it. And if the universe is expanding now, then rewind the clock, and everything must have been closer together. Go back far enough, and all of space, all of matter, all of energy, everything that is, was, or ever will be, was compressed into an infinitesimal point. A singularity. A beginning. This was the birth of the Big Bang Theory, not with a bang, but with a slow, reluctant acceptance of what the data demanded. And yet, the idea did not come easily. Even the equations had whispered it for years before anyone dared to listen. In 1915, Albert Einstein published his theory of general relativity, a revolutionary description of gravity as the curvature of space-time. When he applied his equations to the universe as a whole, they predicted something disturbing. The cosmos could not remain static. It must either expand or contract. But Einstein, like nearly everyone else, believed in a steady, eternal universe. So he did what scientists sometimes do when reality conflicts with expectation: he fudged the math. He introduced a cosmological constant, a kind of anti-gravity force that would balance the equations and keep the universe stable. But when Hubble's observations confirmed expansion, Einstein abandoned the constant. He later called it his greatest blunder. Not because it was bad math, but because he had let his assumptions blind him to a deeper truth. The universe was not eternal. It had a beginning. And that beginning, what could it have been? We call it the Big Bang, but the name is misleading. It suggests an explosion, a fireball erupting into emptiness. But there was no emptiness. There was no outside. There was no time. The Big Bang was not an event in space and time. It was the emergence of space and time. Before it, there was no before. No clock to tick. No void to fill. No observer to witness it. The singularity, the point of infinite density and temperature, was not a place. It was the origin of all places. This is where language fails. Where imagination stumbles. We are creatures of time. We think in sequences, first this, then that. Cause, then effect. But at the beginning, there was no sequence. No cause. No then. Only a sudden, unfathomable transition from nothingness to something, though even nothingness may be too generous a word. Because to imagine nothing, we usually picture empty space, a dark void, infinite and silent. But that is still something. Space. Dimensions. A framework. The true nothing before the Big Bang would have had no space, no time, no laws of physics, no possibility of existence at all. Can you imagine that? Not darkness. Not silence. Not emptiness. But the absence of all three. No stage. No play. No audience. Just not. And then something. We don't know how. We don't know why. The laws of physics break down at the singularity. General relativity, our best theory of gravity, cannot describe the first fraction of a second. Quantum mechanics, which governs the very small, may hold clues, but we lack a theory that unifies them both. The moment of creation lies beyond the reach of current science, hidden behind a veil of mathematical infinity, and yet, we see its echo. The cosmic microwave background radiation, faint afterglow of the early universe, detected in 1965, glows in every direction, a relic of the hot, dense state just 380,000 years after the Big Bang. The abundance of light elements like hydrogen and helium matches predictions of nucleosynthesis in the first minutes. The large-scale structure of galaxies, their distribution across the cosmos, aligns with models of expansion from a single origin. The evidence is overwhelming. the universe had a beginning. But what does that mean for us? If the universe began, then everything that followed, stars, planets, life, consciousness, is a consequence of that initial moment. We are not just in the universe. We are of it. The carbon in your cells, the oxygen in your breath, the iron in your blood, these were forged in the hearts of ancient stars, which themselves formed from the primordial soup of the Big Bang. You are made of stardust, yes. But more profoundly, you are made of time. Of the unfolding of a story that started with a single, incomprehensible event. And yet, the question lingers, what caused it? Science can describe how the universe evolved from a hot, dense state to the vast cosmos we see today. But it cannot answer why there is something rather than nothing. Some physicists suggest the universe arose from a quantum fluctuation in a pre-existing vacuum. Others propose eternal inflation, a multiverse where countless universes bubble into existence endlessly. Still others suggest time itself is cyclical, with big bangs and big crunches repeating in an eternal loop. But all of these ideas, however elegant, push the mystery one step further back. What caused the quantum vacuum? What governs the multiverse? What sets the laws of physics in motion? At some point, the chain of causality must end. And when it does, we enter the realm not of science, but of wonder. Because science is built on observation, on testable predictions, on evidence. But the origin of the universe may lie beyond observation. There is no experiment we can run, no telescope we can build, that can peer before time began. The beginning is not just distant. It is transcendent. It is the boundary of knowledge. And in that boundary, philosophy and science meet. Some see the Big Bang as evidence of a creator, a divine moment of creation. Others see it as a natural event, inevitable in a deeper, unseen reality. Still others accept that we may never know, and find peace in the mystery. But perhaps the most humbling truth is this: the universe did not have to exist. It did not have to begin. It did not have to produce stars, or planets, or life. And yet, here it is. Here you are. Breathing. Thinking. Wondering. Can you feel the weight of that? Not just your body, heavy with sleep, but your existence, suspended in a cosmos that could have been nothing at all. Let your mind drift into that silence. Not the silence between sounds, but the silence before sound. Before light. Before time. A silence so complete it has no name. And from that silence, movement. Expansion. Light. A universe unfolding. And within it, a single planet, orbiting an ordinary star, where a mind now contemplates its own origin. You are not separate from the Big Bang. You are its echo. Its memory. Its possibility. And as you rest here, on the edge of sleep, let go of the need to understand. You do not have to solve the mystery. You only have to be part of it. Because if the universe began from nothing, perhaps matter itself is an illusion. From the void, particles flicker in and out of existence. Next, the vacuum that isn't empty. Close your eyes. Imagine a room. Not just any room, this one has been emptied completely. The furniture is gone. The air has been pumped out. Every atom, every speck of dust, every photon of light has been removed. There is no sound. No light. No heat. No pressure. Nothing moves. Nothing exists. This is not just empty space. This is perfect emptiness. A void so complete it feels like the absence of possibility itself. And yet, according to the laws of quantum physics, this void is not still. It is not silent. It is not empty. It is boiling. Not with heat, not with motion as we know it, but with a frenzy of spontaneous creation and annihilation. Particles flicker into existence, pairs of matter and antimatter, appearing from nowhere, colliding, and vanishing in a fraction of a second. They do not come from anywhere. They do not go anywhere. They simply are, for the briefest moment, before dissolving back into the fabric of space. These are not real particles in the way an electron or a proton is real. They are virtual, ephemeral ripples in the underlying fields that permeate all of reality. And they are everywhere. Even in the deepest vacuum of intergalactic space, even in the silence between your thoughts, space is alive with this invisible storm. This is the quantum vacuum. And it is not empty. For centuries, we thought of space as a passive stage, a neutral backdrop against which the drama of matter and energy played out. Newton saw it as absolute, infinite, unchanging. Even after Einstein revealed that space could bend and stretch, we still imagined it as something fundamentally there, like a canvas. But quantum mechanics shattered that illusion. It revealed that what we call empty space is not passive at all. It is the most active place in the universe. At the heart of this revelation is the Heisenberg uncertainty principle, one of the cornerstones of quantum theory. It states that certain pairs of properties, like energy and time, cannot both be known with perfect precision. The more precisely you know one, the less precisely you can know the other. Applied to empty space, this means that energy cannot remain perfectly zero for any length of time. There will always be tiny, random fluctuations, brief surges of energy that appear and disappear too quickly to be directly observed. And because energy and mass are equivalent, thanks to Einstein's E=mc², these fluctuations can briefly manifest as particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, photons and more. These virtual particles are not just theoretical curiosities. They have measurable effects. One of the most striking is the Casimir effect, predicted in 1948 by Dutch physicist Hendrik Casimir. Imagine two uncharged metal plates placed extremely close together in a vacuum, so close that only a few nanometers separate them. According to classical physics, nothing should happen. No force. No movement. But quantum physics tells a different story. The space between the plates restricts the wavelengths of virtual photons that can exist there, while the space outside allows a wider range. This creates a pressure imbalance. The virtual particles outside push the plates together more than those between them can push outward. And so, the plates slowly move toward each other, as if pulled by an invisible hand. This has been experimentally confirmed. The force is tiny, but real. And it proves that the vacuum is not nothing. It is a dynamic, seething medium, teeming with transient energy and fleeting particles. The emptier the space, the more this quantum activity dominates. In a sense, the universe is never more alive than when it appears to be completely empty. But the implications go far beyond laboratory experiments. If the vacuum is not truly empty, then what is it? Modern physics describes the universe not as made of particles, but of fields, invisible, omnipresent entities that fill all of space. The electromagnetic field, the electron field, the Higgs field, each corresponds to a type of particle. What we call a particle is simply a localized excitation in its field, like a wave on the surface of the ocean. And even when no real particles are present, the fields still exist, vibrating with quantum fluctuations. The vacuum is not the absence of fields. It is their ground state, the lowest possible energy, but not zero activity. This leads to one of the most unsettling ideas in cosmology, that our universe may be unstable. The vacuum we live in, the one that allows atoms, stars, and life to exist, might not be the true, lowest energy state of reality. It might be a false vacuum, a temporary configuration that could, at any moment, decay into a more stable state. If that were to happen, a bubble of true vacuum could form somewhere in space and expand at the speed of light, rewriting the laws of physics as it goes. Inside this bubble, atoms might not hold together. Chemistry might be impossible. Life, as we know it, would cease to exist. And there would be no warning. No alarm. One moment, the universe is as it has always been. The next, everything changes. The constants of nature, gravity, electromagnetism, the strength of nuclear forces, could be different. We would not survive the transition. And yet, according to some theories, this is not only possible, it may be inevitable, given enough time. But here's the deeper mystery. If the vacuum is so active, could our entire universe have emerged from it? Some cosmologists suggest that the Big Bang was not the beginning of everything, but the result of a quantum fluctuation in a greater, timeless void. In this view, universes bubble into existence constantly, like foam on the surface of an infinite ocean. Ours is just one such bubble, a temporary excitation in a deeper, unseen reality. If so, then we are not just made of stardust. We are made of nothingness, a ripple in the quantum foam that underlies all existence. This idea blurs the line between something and nothing. It suggests that nothing is not a static void, but a fertile ground from which universes can spontaneously arise. The same uncertainty principle that allows virtual particles to flicker in and out of existence on a tiny scale might, under the right conditions, allow an entire cosmos to emerge. And if so, then the question why is there something rather than nothing may have a startling answer, because nothing is inherently unstable. It cannot remain empty. It must give rise to something. Let that sink in. Even in silence, the universe hums. Not with sound, but with potential. With possibility. With the quiet, ceaseless churn of creation and annihilation that underlies all of reality. The stillness you feel in the dark, the quiet between heartbeats, the pause before a thought forms, this is not emptiness. It is the surface of a deep ocean, rippling with unseen currents. The vacuum is not dead. It is alive with the pulse of existence itself. And in that aliveness, there is a kind of comfort. You do not need to fear the void. Because the void is not empty. It is full, not of things, but of becoming. Of change. Of the constant, gentle pressure of the universe unfolding, even in stillness. Think of the space between stars. Vast. Cold. Dark. Trillions of miles with no atoms for light years. And yet, that space is not passive. It is filled with quantum fields, with virtual particles, with the faint glow of the cosmic microwave background, with the pull of dark energy accelerating the expansion of space itself. Even in the most desolate regions of the cosmos, reality is active. It is doing something. And so are you. Even when you are still. Even when you are silent. Even when you feel empty. You are not nothing. You are part of the hum. The same quantum fields that fill the vacuum are within you. The electrons in your atoms are excitations of the electron field. The light you see is a ripple in the electromagnetic field. Your body, your mind, your breath, all of it arises from the same underlying fabric that makes the vacuum seethe with life. You are not separate from the quantum foam. You are a slow, complex, conscious expression of it. And as you lie here, drifting towards sleep, let yourself rest in that truth. You do not need to hold on to anything. You do not need to fill the silence. The universe is already full. It has always been full. Even in nothingness, there is creation. Even in darkness, there is light, flickering, momentary, but real. Even in the void, the story continues. Because from the void, stars are born. But stars, too, were misunderstood. Once thought to be eternal lights, we now know they die. And in their death, they create us. Next, the stars that lied about their nature. For as long as humans have gazed upward, the stars have been symbols of permanence. They shimmered in the night sky, unchanged across generations, across civilizations. Kings rose and fell. Empires crumbled. Forests turned to deserts. But the stars remained. Fixed. Eternal. Divine. Ancient poets called them the eyes of the gods. Philosophers saw them as perfect, unchanging spheres in a celestial realm beyond decay. Even early astronomers, peering through primitive telescopes, assumed the heavens were immune to the ravages of time that governed life on Earth. The stars were not born. They did not age. They simply were. But in the quiet hum of 20th century observatories, that illusion began to fade. With better instruments, deeper photographs, and the emerging science of spectroscopy, astronomers discovered something astonishing. Stars are not eternal. They are born. They live. They die. And in their deaths, they give rise to everything we know. This revelation did not come all at once. It unfolded slowly, like a story written in light. In the early 1900s, scientists began to understand that stars shine not by some divine fire, but by nuclear fusion, the violent merging of atomic nuclei in their cores. In the crushing heat and pressure at the heart of a star, hydrogen atoms collide with such force that they fuse into helium, releasing vast amounts of energy in the form of light and heat. This process, known as the proton-proton chain, is what powers our sun. It has been burning for nearly 5 billion years, converting 4 million tons of matter into energy every second. And for a time, it will continue until the hydrogen runs out. But what happens when a star exhausts its fuel? The answer depends on its size. A small star, like a red dwarf, may burn dimly for trillions of years, slowly cooling into darkness. But a star like our sun will, in about 5 billion years, swell into a red giant, engulfing Mercury, Venus, and possibly Earth in its expanding atmosphere. Then, it will shed its outer layers, forming a glowing shell of gas known as a planetary nebula, while its core collapses into a dense, Earth-sized ember called a white dwarf. It will no longer shine by fusion. It will simply radiate away its stored heat, fading over eons into a cold, dark cinder. But the most dramatic deaths belong to the massive stars, those many times heavier than our sun. These stellar titans burn hotter, faster, more furiously. They consume their fuel in mere millions of years, not billions. And when they finally run out of hydrogen, they do not gently fade. They collapse. The core, no longer supported by the outward pressure of fusion, gives way to gravity's relentless pull. It implodes in a fraction of a second, reaching densities so extreme that protons and electrons are crushed together into neutrons. The outer layers of the star, suddenly unsupported, rebound off the collapsing core and explode outward in a cataclysm of unimaginable power, a supernova. For a brief moment, this dying star outshines entire galaxies. Its light can be seen across billions of light years. And in that final, violent flash, something extraordinary happens. New elements are forged. Not just helium. Not just carbon. But oxygen, nitrogen, calcium, iron, gold, uranium, elements heavier than anything created in the quiet fusion of a stable star. These are born in the inferno of the explosion, where temperatures soar to billions of degrees, and neutrons are captured in rapid succession, building atomic nuclei in a process known as R-process nucleosynthesis. In seconds, the universe gains new building blocks, materials that did not exist before. And then, the star scatters them. The explosion hurls these newly created elements into space, mixing them with interstellar gas and dust. Over millions of years, this enriched material cools, condenses, and collapses under gravity to form new stars, new planets, new possibilities. And in one such cloud, about 4.6 billion years ago, a new solar system began to form. At its center, a modest star ignited, our Sun. Around it, a disk of debris swirled, clumping into rocks, asteroids, and eventually, planets. One of them, small, rocky, far from the center, accumulated water, an atmosphere, and, against all odds, life. And every atom in that life, except the simplest hydrogen, came from a dead star. This is not poetry. It is chemistry. It is astrophysics. When you breathe, the oxygen in your lungs was forged in the core of a red giant. The calcium in your bones was created in a supernova explosion. The iron in your blood, carrying oxygen through your veins, was born in the final moments of a collapsing star, moments before it exploded and died. Even the trace elements, zinc, copper, iodine, are stardust, scattered across the galaxy and gathered into your body over billions of years. You are not just like a star. You are made of them. Every cell, every thought, every heartbeat is a continuation of that ancient cosmic fire. And yet, for most of history, we did not know this. We looked up and saw eternity. We did not see the violence. We did not see the death. We did not see the recycling of matter across time and space. It took the convergence of astronomy, nuclear physics, and chemistry to reveal the truth. We are not separate from the stars. We are their children. This realization carries a profound weight. Because if stars are not eternal, then neither is the universe they illuminate. The night sky, so vast and full of light, is a temporary condition. One day, it will go dark. In the far, far future, trillions of years from now, the era of star formation will end. The gas clouds needed to birth new stars will be exhausted. Existing stars will burn out. White dwarfs will cool into black dwarfs, invisible and cold. Neutron stars and black holes will drift in silence. The universe will become a graveyard of dead stars, lit only by the faint afterglow of the Big Bang, slowly fading into undetectability. This is the heat death of the universe, a state of maximum entropy, where no energy gradients exist, no work can be done, no life can be sustained. Time will continue, but nothing will happen. The cosmos will be dark, cold, and still. And in that context, our existence, our brief, flickering moment of light and life, becomes almost unbearably precious. We live in a narrow window of cosmic history. Not too early, when galaxies were still forming and heavy elements were rare. Not too late, when all the stars are gone. We are here, now, in the middle, when the universe is old enough to have created stars, and young enough for them to still be shining. You are stardust. But you are also time dust, a product of a fleeting alignment of conditions that may never occur again. Feel the weight of that. Not just the physical weight of your body, but the existential weight of being alive at this moment in the 13.8 billion year story of the universe. You are not just a passive observer. You are a participant. A conscious expression of the universe looking back at itself, wondering how it came to be. And in that wonder, there is peace. Because you do not need to last forever to matter. You do not need to be eternal to be real. The supernova that forged your iron burned for only seconds. And yet, its legacy lives on, in you, in the earth, in the possibility of meaning. You are not a mistake. You are not an accident. You are the universe remembering its own history, one breath at a time. And as you rest here, on the edge of sleep, let that truth settle into your bones. You are made of dead stars. You carry their fire in your blood. You speak with a voice shaped by ancient explosions. And when you close your eyes, the same atoms that once burned in the heart of a distant sun now dream of stillness. You are not small. You are not insignificant. You are the universe, awake, breathing, remembering. And as the silence deepens, and the stars fade from your mind's eye, know this, even when the last star dies, the story does not end. Because for a brief, luminous moment, it was known. It was felt. It was loved. And if stars die, so too do species. Once, extinction was unthinkable. But fossils told a different story. Next, the lost worlds beneath our feet. In the quiet halls of 18th century Europe, naturalists arranged their collections with reverence. Shells, bones, preserved insects, each specimen was a testament to the perfection of creation. The world, as they understood it, was a divine design, unchanging and eternal. Every creature had been placed exactly where it belonged by a benevolent hand, and if one could not be found, it was only because it had not yet been discovered. The idea that a species could vanish from the earth, completely, permanently, irreversibly, was unthinkable. It contradicted not only science, but theology. If God had created a creature, how could it simply cease to exist? Extinction would imply imperfection, a flaw in the grand design. And so, for centuries, the possibility was denied. But then, the bones began to appear. Buried in riverbanks, unearthed in quarries, pulled from frozen tundra, gigantic, impossible skeletons emerged from the earth. Creatures with teeth like daggers, tusks like scythes, skulls larger than a man. They did not resemble any living animal. And yet, they were clearly real, too large, too detailed, too anatomically precise to be fabrications. In Siberia, woolly mammoths were found frozen in ice, their flesh still intact, their last meals preserved in their stomachs. In North America, fossilized remains of towering beasts with armored plates and spiked tails hinted at a world that no longer existed. These were not myths. They were not dragons conjured by frightened villagers. They were physical evidence of lives that had once thrived, and then disappeared. At the center of this growing mystery stood a man named Georges Cuvier, a French naturalist of extraordinary intellect and meticulous observation. He studied these remains not with wonder, but with scientific rigor. Comparing the anatomy of fossilized bones to living species, he concluded something radical. These animals were not just unknown, they were gone. Not hiding in unexplored jungles or remote mountains. Not waiting to be rediscovered. They were extinct. Cuvier's work in the late 1700s and early 1800s shattered the illusion of permanence. He identified entire species, mammoths, mastodons, giant sloths, that had once roamed the earth but no longer walked its surface. More than that, he proposed that their disappearance was not gradual, but catastrophic. He believed in catastrophism, the idea that sudden, violent events, like floods or upheavals, had wiped out entire ecosystems, only for new ones to emerge afterward. While his specific mechanisms were later challenged, his central insight held: extinction was real. Life was not immune to endings. This was a profound shift. For the first time, science acknowledged that the history of life was not a steady, unbroken progression, but a series of rises and falls, of flourishing and collapse. The Earth was not a static museum of divine creation. It was a dynamic, ever-changing theater of birth and death on a planetary scale. And then, in the 19th century, another discovery deepened the mystery: dinosaurs. The word itself, meaning terrible lizard, was coined in 1842 by Richard Owen, but the bones had been puzzling scientists for decades. Gigantic femurs, vertebrae the size of barrels, footprints embedded in stone. These were not the remains of elephants or crocodiles. They belonged to creatures of unimaginable scale and strangeness. Some walked on two legs, towering over forests. Others stretched longer than city blocks, their necks reaching into the canopy. They ruled the Earth for over 180 million years, longer than any other dominant species in history. And then, they vanished. For a long time, no one knew why. Theories abounded: climate change, volcanic activity, disease, even the idea that dinosaurs were simply too large to survive. But in the 1980s, a breakthrough came. A layer of iridium, an element rare on Earth but common in asteroids, was found in sedimentary rock dating to exactly 66 million years ago, marking what is now known as the Cretaceous-Paleogene (KPG) boundary. This layer appeared globally, suggesting a worldwide event. The hypothesis, proposed by physicist Luis Alvarez and his son Walter, was staggering. A massive asteroid, about 10 kilometers wide, had struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact unleashed energy billions of times greater than the atomic bomb dropped on Hiroshima. It triggered wildfires, tsunamis, and a cloud of debris that blotted out the sun for months, perhaps years. Photosynthesis collapsed. Food chains disintegrated. 75% of all species on Earth, including all non-avian dinosaurs, perished. This was not just extinction. It was mass extinction, one of at least 5 such events in Earth's history. The largest, the Permian-Triassic extinction 252 million years ago, wiped out over 90% of marine species and 70% of land vertebrates. Volcanic eruptions in Siberia may have released enough carbon dioxide to trigger runaway global warming, acidifying the oceans and suffocating life. Each of these events reset the course of evolution, clearing the stage for new forms to emerge. Mammals, small and unobtrusive during the age of dinosaurs, survived the KPG event and eventually gave rise to primates, and then to us. But here lies the deepest implication: extinction is not an anomaly. It is the rule. Over 99% of all species that have ever lived are now gone. The Earth is a graveyard of lost worlds, buried beneath layers of sediment, encoded in fossils, whispered in the silence between geological strata. Life is not guaranteed. It is fragile. It is temporary. It is always on the edge of vanishing. And yet, we have long resisted this truth. Even after Cuvier, even after the dinosaurs, even after the asteroid hypothesis, we have clung to the belief that we are different. That our intelligence, our technology, our civilization shields us from the fate of the mammoth, the pterosaur, the trilobite. But the evidence suggests otherwise. Because we are now living in the midst of what scientists call the 6th mass extinction, and this time, we are the asteroid. Human activity, deforestation, pollution, overfishing, climate change, habitat destruction, is driving species to extinction at a rate hundreds, perhaps thousands, of times higher than the natural background rate. Entire ecosystems are collapsing. Coral reefs are bleaching. Insects are vanishing. Large mammals are disappearing from the wild. Scientists estimate that we are losing dozens of species every single day. Not because of a cosmic impact or volcanic fury, but because of choices we make, what we eat, how we build, how we live. This extinction is not dramatic. It does not come with fire or thunder. It comes quietly. A frog species in a Central American cloud forest, never named, dies out as temperatures rise. A bird in the Amazon vanishes as its forest is cleared for cattle pasture. A fish disappears from a river dammed for hydroelectric power. No one witnesses it. No one mourns it. The earth simply forgets. And if we continue on this path, what becomes of us? The dinosaurs ruled for 180 million years. Homo sapiens, in our current form, have existed for less than 300,000 years, barely 1% of that time. We have built cities, written symphonies, sent probes beyond the solar system. But none of that guarantees survival. Civilizations rise and fall. Species come and go. The Earth does not care about legacy. It does not preserve monuments. It does not remember names. In 10 million years, if no one is here to dig them up, our cities will be dust. Our books, our art, our satellites, all reduced to scattered atoms, buried under sediment, perhaps fossilized as faint impressions in rock. Future geologists, if any exist, may find a thin layer of plastic, radioactive isotopes, and concentrated carbon, a marker of our brief, intense presence. They may call it the Anthropocene. They may wonder what happened to the creatures who changed the planet so quickly, so completely, and then disappeared. Let your breath slow. Feel the weight of time pressing down, not as a burden, but as a quiet truth. You are alive in a moment of great fragility. Not just your life, but the lives of millions of other species, all interconnected, all dependent on a delicate balance that is now shifting. And yet, there is beauty in this awareness. Because to know that extinction is real is to understand that life is precious. Not because it lasts forever, but because it doesn't. Because it is fleeting. Because it can be lost. The earth forgets even the mightiest. But for now, you remember. You feel the pulse in your wrist. You hear the rhythm of your breath. You are here, awake, in a world still alive with songbirds, with forests, with oceans teeming with mystery. And that is enough. Not to conquer. Not to endure. But to witness. To be part of the story, however briefly. And as you drift towards sleep, let go of the illusion of permanence. You do not need to last forever to matter. You only need to be here, now, breathing in the air that once passed through the lungs of dinosaurs, walking on ground that has cradled countless lives before you. You are not separate from extinction. You are part of its shadow. And its light. And if species vanish, so too do scientific certainties. One of the most shocking reversals came in medicine. Next, the doctors who killed with science. In the dimly lit maternity wards of mid-19th century Vienna, a quiet horror unfolded behind closed doors. Women came to give birth, full of hope, anticipation, the sacred expectation of new life, and instead, many left in coffins. The disease had no name, but its symptoms were unmistakable: high fever, chills, abdominal pain, a rapid decline into delirium and death. It was called childbed fever, or puerperal fever, and in some hospitals, it claimed the lives of up to 30% of new mothers. Entire wards reeked of decay. Nurses whispered in fear. Doctors, baffled and helpless, called it fate, divine punishment, or the influence of bad air, miasmas rising from the sewers and swamps of the city. But one man refused to accept that explanation. His name was Ignaz Semmelweis, a young Hungarian physician working in the maternity clinic of the Vienna General Hospital. He was not a revolutionary by nature. He was meticulous, observant, deeply troubled by the suffering he witnessed. And in 1847, he noticed something that no one else had. The mortality rate was drastically different between two nearly identical wards. In one, run by doctors and medical students, the death rate from childbed fever hovered around 10 to 18%. In the other, staffed by midwives, it was less than 2%. The same building, the same city, the same water, the same food. The only difference? The people who delivered the babies. And then, a clue. A colleague of Semmelweis's, a forensic pathologist, accidentally cut his finger during an autopsy and soon died of symptoms identical to those of childbed fever. Semmelweis was struck by the similarity. He began to suspect a connection. Perhaps the doctors and students, who routinely performed autopsies on women who had died of the fever, were carrying something, some invisible agent, from the dead bodies to the living mothers. They would move from the morgue to the delivery room without washing their hands, their fingers still stained with bodily fluids, their fingernails caked with unseen residue. And then they would deliver babies, cutting open the cervix with those same contaminated hands. It was a radical idea. Not because it seemed obvious in hindsight, but because it contradicted everything medicine believed at the time. The dominant theory of disease was miasma, the idea that illness arose from corrupted air, from foul odors, from environmental imbalances. There was no concept of germs, no understanding of microorganisms, no knowledge of bacteria or viruses. The microscope existed, but it was not yet used in medicine. The idea that invisible particles could cause disease was not just unproven, it was unthinkable. And yet, Semmelweis acted on his intuition. He demanded that all doctors and students wash their hands in a solution of chlorinated lime before entering the maternity ward. It was not a perfect method, lime was harsh, the solution stung, and compliance was inconsistent, but the results were immediate and staggering. Within months, the mortality rate in the doctor's ward plummeted from 18% to less than 1%. It was a 90% reduction in deaths. A medical miracle, achieved not with new drugs or surgeries, but with soap and water. But instead of celebration, Semmelweis was met with hostility. His colleagues mocked him. They resented being told they were responsible for the deaths of their patients. They bristled at the implication that their hands trained in anatomy, revered as instruments of healing, could be carriers of death. How could gentlemen, educated men of science, be compared to butchers or charlatans? The idea was offensive. It challenged not just medical theory, but social hierarchy, professional pride, and the very identity of the physician. Worse, Semmelweis could not explain how it worked. He had no mechanism, no germ theory, no microscope images of bacteria. He could only point to the data, to the lives saved, to the undeniable drop in mortality. But in science, correlation is not enough. Without a theory, without a framework, even the most compelling evidence can be dismissed as coincidence. He published his findings. He pleaded with hospital administrators. He argued with colleagues. But the medical establishment closed ranks. He was denied promotion. His contract was not renewed. He was forced to leave Vienna, returning to Budapest in disgrace. There, he continued his work in obscurity, implementing hand-washing in a smaller hospital and again reducing mortality. But his voice grew more desperate, more strident. He wrote angry letters to prominent doctors, calling them murderers for refusing to adopt his methods. He became isolated, erratic, consumed by the injustice of it all. In 1865, at the age of 47, he was committed to an asylum under suspicious circumstances, some say by colleagues who wanted him silenced. 2 weeks later, he died of sepsis, likely from an infected wound sustained during a beating by guards. The irony was unbearable. The man who had discovered how to prevent deadly infections died from one. It would take nearly 2 decades for the world to catch up. In the 1870s and 1880s, Louis Pasteur established germ theory, proving that microorganisms caused fermentation, disease, and decay. Joseph Lister, inspired by Pasteur, introduced antiseptic surgery, using carbolic acid to sterilize instruments and clean wounds, dramatically reducing postoperative infections. Robert Koch identified specific bacteria responsible for tuberculosis, cholera, and anthrax. The invisible world that Semmelweis had sensed but could not see was finally revealed. And only then did the medical community admit he had been right. But the cost of that delay was incalculable. Hundreds of thousands of women, perhaps millions, died needlessly in the years between Semmelweis's discovery and its acceptance. Entire generations of mothers, sisters, daughters, lost not to ignorance, but to arrogance. Not to lack of data, but to the refusal to believe it. This was not just a failure of science. It was a failure of humanity. Because science is not a pure, self-correcting machine. It is made of people. People with egos. People with reputations. People invested in the status quo. People who resist change, especially when it implies they have been wrong, dangerously wrong, for years. Semmelweis's story is a warning. Not just about hand-washing, but about the fragility of truth in the face of institutional inertia. He had the evidence. He had the results. He had the moral imperative. But he lacked the language, the theory, the social capital to make his case stick. And so, he was silenced. And we must ask, how many Semmelweises walk among us today? How many researchers, clinicians, thinkers, are dismissed because their ideas challenge orthodoxy? Because they come from the margins? Because they lack the right credentials, the right accent, the right gender, the right institution? How many breakthroughs are ignored, not because they are false, but because they are inconvenient? Because they threaten funding, power, or prestige? Consider the early warnings about climate change. The ignored reports on opioid risks. The suppression of research on tobacco. The dismissal of patient-reported symptoms in chronic illnesses like Lyme disease or long COVID. Again and again, we see the same pattern. Truth emerges, is resisted, is ridiculed, and only accepted after damage has been done. Science prides itself on being self-correcting. But the correction often comes too late. After the preventable deaths. After the ecosystems collapse. After the trust erodes. And perhaps the most dangerous thing in science is not ignorance, but certainty. The certainty that we already know. The certainty that our models are complete. The certainty that anyone who disagrees must be wrong. That is the mindset that rejected Semmelweis. That is the mindset that delayed the acceptance of plate tectonics, of the link between smoking and cancer, of the reality of mental illness. But here, in the quiet aftermath of this story, there is also a kind of peace. Because Semmelweis, though broken, was not forgotten. His name lives on. Not just in medical textbooks, but in the simple act of washing your hands. Every time you lather up before a meal, after using the restroom, before touching a wound, you are honoring his legacy. You are enacting his insight. You are participating in a ritual of care that began with one man's refusal to accept suffering as inevitable. And in that ritual, there is humility. The humility to admit we do not know everything. The humility to listen to the data, even when it contradicts our beliefs. The humility to change our minds. The humility to wash our hands, not just physically, but intellectually, before we touch the lives of others. Let this truth settle in. Not as a condemnation, but as a reminder. You do not have to be right all the time. You only have to be willing to be wrong. You do not have to have all the answers. You only have to care enough to ask better questions. And as you lie here, drifting towards sleep, feel the warmth of water on invisible skin. The scent of soap. The rhythm of your breath. You are safe. You are clean. And somewhere, in the silence between heartbeats, a long-dead doctor smiles. Because you listened. And if science can kill with ignorance, it can also promise salvation it can't deliver. From germs to genes, we now face a new frontier. Next, the hubris of genetic determinism. For much of the 20th century, we were told a story about ourselves, a story so compelling, so seemingly scientific, that it shaped medicine, identity, and even our deepest sense of self. You are your genes. From the moment of conception, the double helix within each of your cells was said to contain the complete blueprint of your life. Your height, your eye color, your risk of disease, your temperament, even your intelligence, your talents, your predisposition to addiction or mental illness. These, we were told, were written in the silent language of DNA, an unchangeable code passed down through generations, dictating the boundaries of who you could become. We called it genetic destiny. And for a time, it felt like truth. But what if that story was only half complete? What if the code is not a fixed script, but a living, responsive instrument, one that plays differently depending on the hands that touch it? Imagine a grand piano, perfectly tuned, its keys polished, its wood gleaming. The instrument is flawless. The notes it can produce are fixed, each key corresponds to a specific tone. But the music that emerges? That depends on the musician. On their mood. Their training. The piece they choose to play. The same piano can produce a lullaby or a storm, a whisper or a roar. The instrument does not change. The keys remain the same. But the expression is infinite. This is the emerging understanding of epigenetics, the science of how genes are regulated, not altered. Epigenetics does not change the DNA sequence. It doesn't rewrite the letters of the genetic code. Instead, it controls which genes are turned on or off, how loudly they speak, and when they fall silent. It does so through chemical tags, methyl groups and histone modifications that attach to DNA like switches, responding to signals from the environment, what you eat, how you sleep, whether you've been loved or wounded, whether your ancestors lived through war or famine. And the most astonishing part? These changes can be passed down. Not through mutation, but through inheritance of the settings, the volume knobs, the mute buttons, on the genetic machinery. You are not just shaped by your own life. You carry echoes of your parents' choices, your grandparents' struggles, even the silent imprints of great-grandparents you never met. One of the most powerful examples comes from history itself. During the final winter of World War II, the Netherlands was gripped by a brutal famine known as the Hunger Winter. Food supplies collapsed. People ate tulip bulbs, sugar beets, anything to survive. Pregnant women endured extreme malnutrition. Decades later, scientists studying the children born during that time discovered something remarkable. They had higher rates of obesity, diabetes, and heart disease. But even more surprising, so did their children, the grandchildren of the famine survivors. The trauma of starvation, experienced by a mother, had altered the epigenetic markers in her unborn child, and those changes persisted into the next generation. The body, it seemed, had learned to expect scarcity, and held onto that memory, even in times of plenty. This is not science fiction. It is evidence that experience can become biology. That the environment doesn't just influence your behavior, it rewires your gene expression in ways that can ripple across lifetimes. And then there are identical twins, two people with the same DNA, born from the same egg, sharing 100% of their genetic code. As children, they are nearly indistinguishable. But as they age, something shifts. One may develop cancer, the other remain healthy. One may struggle with depression, the other thrive. One may be slender, the other overweight. One may live decades longer. How is this possible if genes are destiny? The answer lies in epigenetics. As twins live different lives, one smokes, the other doesn't. One faces chronic stress, the other finds peace. One eats well, the other poorly. Their epigenetic profiles diverge. The same genes are present, but they are expressed differently. Their bodies begin to read the same script in two distinct voices. And over time, those differences accumulate, shaping health, aging, and even identity. This realization dismantles one of the most persistent myths of modern biology, that we are prisoners of our DNA. That our fate is sealed at conception. That free will is an illusion, and all we are is the sum of our inherited code. Epigenetics tells a different story, one of agency, adaptability, and profound interconnection. You are not merely what you inherited. You are what you do with it. And that changes everything. Because if genes are not destiny, then healing is possible in ways we once thought impossible. A person with a genetic predisposition to heart disease may never develop it if they eat well, exercise, and manage stress. Someone with a family history of depression may build resilience through therapy, mindfulness, and connection. The genome is not a prison. It is a conversation, one that continues throughout your life, shaped by your choices, your relationships, your environment. But this power comes with weight. If we are not bound by our genes, then how responsible are we for our health? If trauma can be passed down, can healing be, too? And if we can influence our gene expression, where do we draw the line between self-improvement and self-coercion? Consider the rise of biohacking, of genetic testing, of wellness culture. People scan their DNA to predict their future, then obsess over diet, sleep, and supplements to optimize their biology. There is value in this awareness, prevention, empowerment. But there is also danger. The risk of blaming individuals for conditions shaped by poverty, trauma, or systemic injustice. The idea that if you're sick, you simply didn't try hard enough. That if your genes are on, it's your fault for not turning them off. Epigenetics, meant to liberate us from genetic determinism, could be twisted into a new form of biological guilt. And what of the future? As we learn more about epigenetic editing, ways to deliberately alter gene expression, will we begin to engineer not just our bodies, but our descendants? Will parents one day be expected to optimize their children's epigenomes before birth? Will society judge not just your actions, but your biological choices? These are not distant questions. They are already here. But in the quiet space between science and soul, there is also peace. Because epigenetics reveals something beautiful, you are not a passive recipient of your biology. You are in dialogue with it. Every choice you make, what you eat, how you love, whether you rest or rage, sends signals into your cells, whispering to your DNA, shaping how it behaves. You are not just living your life. You are directing it, at the molecular level. And that means you are not doomed. You are not fixed. You are not finished. You are becoming. Even now, as you lie here, breathing slowly, your body is listening. The softness of a blanket, the rhythm of your breath, the safety of this moment, these are not just comforts. They are signals. They tell your cells, you are not under threat. You can rest. You can heal. Stress hormones ease. Inflammation calms. Repair mechanisms activate. Your genes respond not with fear, but with quiet restoration. This is the power you carry. Not magic, not wishful thinking, but biology, alive, responsive, and deeply wise. And as you drift, consider this: you are not just what you inherited. You are what you choose to become. Not in a single grand decision, but in the small, quiet acts of daily life. In the meal you choose. In the breath you take. In the way you treat yourself when no one is watching. In the love you allow. In the forgiveness you offer. In the stillness you cultivate. You are writing your story, not just in memory, not just in emotion, but in the very chemistry of your being. And that story is not over. It is unfolding. With every heartbeat. With every breath. And in the silence between them, a new possibility stirs. You are not bound. You are not broken. You are not behind. You are here. Alive. Listening. Changing. And as sleep gently takes you, know this: the code within you is not your master. It is your companion. And together, you are learning how to live.